So there are 6 things I was going to talk about this morning. I just want to talk about them. They're quite awesome to me and they seem quite wonderful. The first is I want to talk about the medical uses of an element that doesn't exist naturally on Earth. I want to talk for a little while about some nuclear reactors that nature designed. And I want to discuss then, thirdly, will be the medical uses of antimatter. We'll talk about targeting cancer in some of these applications. We need to talk about the mystery of neutrinos and alpha emitters in therapy. So that's the scheme. And I'll only have time to spend about 5 minutes on each, 10 minutes on each. So let's start with something that doesn't exist on, First of all, just to give you some vocabulary, there are 3 kinds of radiation that we talk about. There's gamma radiation, which is pure energy waves. There's beta radiation, which is electrons, and alpha radiations, which are helium nuclei, and they're sort of big and have a lot of energy. Now, you know this table of the elements from your school days, and the amazing thing was that this table of elements is not just the table of elements that we know of, it's the table of elements of all the elements that can exist. And when Mendeleev was laying this out and he discovered there were blanks in the table because he didn't know all of the elements at the time, he made predictions which were borne out. For instance, he predicted the existence of iodine. And he predicted another one over here that I haven't shown you yet. And that brings us to technetium, which was discovered in 1937. That's or created, I guess, by these 2 guys. And they made it by irradiating molybdenum in a reaction, and they made technetium. They were not allowed the credit of claiming the discovery because in those days you had to make enough of, if you claimed a new element, you had to purify enough so that you could do the melting point and the crystalline types and all of that. And with technetium, you can't do it because there is so little of it being made. There are these 45 isotopes of technetium that are possible in the universe. All of them are radioactive, and so they all decay. The one that we are talking about today is called technetium-99m. It has a short half-life of about 6 hours, and so we can get rid of it without contaminating the environment. And it has very good chemistry, so you can make many things with it to make drugs that go to specifically to organs of interest and diseases of interest, and it's not that expensive. Anyway, so there it is. We discovered it, and here we are. Now, historically, in all the time that I've been in nuclear medicine, technetium was made by irradiating weapons-grade uranium. We would buy each week at Chalk River, we would buy a sort of pencil-sized amount of uranium-235. And because we had it on site, there was lots of American security to guard against accidents and losses. And you would irradiate that pencil of uranium for a few days and then take it out of the reactor and then extract the molybdenum, which has only 3.5-day half-life, and you could make it into a product that could be shipped to customers and it would go to hospitals around the world. For many decades, Canada was the world's leading producer of technetium, but then we had to shut down the NRU reactor because it was the oldest functioning research reactor in the world, and it was beginning to have problems like corrosion and the like. And so in recent years, we've been buying wherever you can get it, I guess, from Europe and South Africa even. And we've been trying to create other means of production, but no, I'm not aware yet that any of these have been successfully or perhaps economically developed. The shutting down of the reactor caused a fuss in the US, and they set up a committee in Congress to investigate the difficulty that the US was in. And I well remember that at one point, one of the senators asked the question, how much technetium are we talking about? Is it a gram or a pound or a ton? And the answer given to him was, well, if you can make all the technetium that you need for a year, and put it in a crack in time where it wouldn't decay until you need it, doing 100,000 examinations a day, that one, about a gram, would do you for a year. So there are not too many molecules of radioactive technetium in a single clinical dose. And so that's about the way the business is going on around the world, at about 100,000 scans every day. Now, here are just some pictures to show you the kinds of things that one sees. This is an individual who's had a serious accident at some time in the past. Probably it looks to me like someone who wasn't wearing a seatbelt and who jammed their knees against the dashboard in a head-on crash and then broke both hips and damaged the knee. And all of this dark material that you see here is hypertrophic calcium, extra calcium being laid down, that's hindering the movement of the joint. And until, for as long as the scan takes up the technetium in these cases, the disease will recur if they remove it. So they have to wait until the scan becomes negative, and then the individual can undergo some restorative surgery. Here's a heart scan that's happened to more than a few of us, I think. This is an agent.
Al, we're not seeing your screen.
You're not seeing my screen. Why didn't you say something earlier?
Well, I am.
Okay, let's stop for a minute. I'm on. There we are. I have your.
Al, can you go back a couple of screens just to keep us up to date?
Okay. I have to go back up to PowerPoint. Are you seeing my screen now?
No.
Okay, let me just put it down. Okay. I have to find. Do you see it now?
Nope. Are you using the share screen?
Yes.
Okay, and the icon up in the left-hand corner, and then you press down on the share screen. So you got two buttons.
Yeah. Okay, up in the left-hand corner, right in the corner.
Yep, just press on it once.
And
then go down to the bottom on the right-hand corner. There's a share screen.
Okay.
There you go.
Okay. Now we're in?
Yep.
I am so sorry. Okay, now we gotta go up there. Okay. So everybody sees this now? Okay. Now this is a heart scan that was done with technetium product that shows that when the individual is resting, they have normal blood flow to the heart muscle. And when they had been stressed on the bicycle or on a treadmill, that they have a defect in the inferior wall of their heart. And this is the kind of surgery that would require some vascular restoration. Yeah, okay. Now, this was the bones that I talked about, okay? All right, now then, and here is a thyroid scan. And this is an area which doesn't take up technetium. and that needs to be considered for a biopsy because it might be a cancer. Now, I told you there's no natural technetium in the world. I sort of lied a little bit, but that was because I just couldn't tell two stories at once. And so this is the sidebar. After the Second World War, the world was being surveyed for sources of uranium, and there was a large store of it in Gabon in West Africa. And some geologists there were looking through some of their drill sites, and they came across this strange phenomenon that the rock formation they were looking at, they knew was hundreds of millions of years old. But when they examined the composition of the rock, someone said it looks more like depleted uranium. It looks more like old reactor fuel. And so, and here's a site in the mine. The yellow is uranium hydroxide, which is the natural form of uranium in this mine. The thing that had been going on in Gabon several billion years ago was that there was a very rich vein of uranium that happened to run in a riverbed, and in those times the uranium enrichment would have been about what reactor fuel is like today. So as the water ran down the riverbed, it acted as a moderator that slowed the neutrons down, and they reacted more with the uranium that was already there. And then it would happen periodically that the river would boil away, the bed would go dry, and then the reaction would stop. And then when things cooled down, the water came back and they'd go off again. So this thing ran, we think, about 100 million years. And there were a total of 17 natural reactors that were discovered in the beds of the Okla River. And they've all been mined out now because the French in particular were concerned to build lots of reactors since they had no coal or natural gas in France. Okay, I want to go on to the second topic, and that would be take us to talk about, I want to talk about antimatter. This will lead up to that. If you've ever had the privilege of visiting CERN in Switzerland, the big reactor collider, they have a huge machine there that runs for 25 kilometers through the mountains and forms a perfect circle. They bang hydrogen protons together at very high speeds, the speed of light, and look at the debris that comes out. And they do this about 40 million times a second to understand the nature of matter better. What we have here is the sort of artist's rendition of what comes out of that sort of a collision. And you'll notice that some of these yellow lines are going in a straight line. Those are energetic particles that do not have an electric charge. And some of them are curved, like this one and this one and this one. They have an electric charge, and they could be electrons or positrons, that is positively charged electrons. Now, it turns out that whenever we do an experiment like this, it's actually exactly 50% electrons and positrons. That is antimatter. And the antimatter, we believe this is mimicking the moment of creation. And the antimatter, we think, in the actual creation event disappeared inside of a few seconds. But we don't know exactly what happened to it should be that when matter collided with antimatter, that both were destroyed. And yet all the antimatter is gone. There's a little matter left, which is us and everything we know. And we don't know why it wasn't quite an even break, why 1/10 billionth part of the first dollop of matter remains. And there are still theoretical physicists around who spend their nights lying awake thinking about why this is and why we have any business being here at all, because it should have evened out. But that's how it is. That's a pure mystery still. And so why are we here? That's correct. Now, just a moment to take you aside. This blue line that you see here is a demarcation of all the normal non-radioactive isotopes of all the elements scattered out here in order of their size, their mass, going from hydrogen to helium at the top. And everything that's to the left of the blue has too few neutrons. And so when it undergoes decay, it becomes, it undergoes a positron decay. And when it goes to the right, it's because it had too many neutrons and it decays by beta decay. So we live on this thin blue line, and all the yellow boxes here are isotopes of the elements that can be made in reactors and accelerators. Now, to tie this into cancer, one of the features of cancer cells is that they cannot use oxygen very well. So they're very, very hungry for glucose, and they like to just ferment the glucose to get a couple of bursts of energy, but most of it they leave behind because they're not good at using the oxygen. And so cancer cells are very, very hungry for sugar. And when we want to examine how cancers have spread, we can use glucose that has been chemically modified to put a fluorine atom in place of hydrogen. And then this will go in just like sugar into the cancer cells, but it can't go any farther because the enzymes won't break off the fluorine. And so it gets trapped, and then you can make images of where the cancer is. And this is a PET CT scanner, nothing special about that. But I should tell you that when I was toward the end of my career, I reckoned once I'd spent 1,000 hours over a couple of years talking to government people about allowing us to deploy PET scanners in medical practice in Ontario. And in my time, it did not succeed. And others who were more persuasive, or maybe cancer was more persuasive, finally let it happen. But here's an example of how the imaging helps. You can see on the left is a CT scan, which is just X-rays and densities. And if you look very, very carefully, there's a little density, a little shadow in here, but you might on a busy day walk by it. If you look at the PET scan, it shows you that there's a huge area here, a volume that is taking up the radioactive sugar. And then you can put it on top of the X-ray and show exactly where it is. It is indeed this mass here. And so that's how we use antimatter in medicine. Here's an example of someone whose lymph nodes in the chest are taking up the sugar. And I don't know whether this is a lymphoma or whether it's a secondary from lung cancer or something else. I don't have that information. But there you see very clearly what you don't see clearly in the shadow of the heart and the big blood vessels on the X-ray. There are some other things that you can do. You can label drug called fluoridopa with fluorine, and you can show these structures in the brain that we call basal ganglia. And this is a normal basal ganglion. And over here, this is a patient with Parkinson's disease. And so we're seeing that there's a change, and there has been clinical use made of this. And here is a patient with Alzheimer's disease who has been given another drug that's labeled with fluorine 18, again, fluorine, positron emitter. On the left is a normal PET scan, and on the right is a patient who has Alzheimer's disease. And we've been looking for many years for something that we could, cheap and easy, that we could use to identify people with Alzheimer's disease. We don't quite have it yet, but it's coming, I think. Now, I want to talk about something, just to touch on therapy. Neuroendocrine tumors. There are tumors that make chemicals that make us feel sick, and we call them neuroendocrine tumors. And we have drugs that, here's a drug that localizes DOTA-talk, it's called, localizes in tumors, and you can label it with a gallium-63, which is a PET emitter. It's one of those PET isotopes, and you can see that the tumor is in this vertebral body here, and you can then label it with yttrium-90, which is a beta emitter and doesn't show through the tissue very well. You can't image it at all well, but we know that we got this therapeutic drug into this bone marrow metastasis and into this lymph node metastasis that's down here. Okay, so now I want to talk a bit about alpha emitters. This is kind of fun. There. Now, if you look at this periodic table, over here there's a compound, an element called astatine. Astatine, to my mind, is really quite amazing. I remember reading about astatine a while back, and the writer, to impress on us how rare it is, made the suggestion that in the whole universe, there might at any one time be only about 1 tablespoon of astatine. That's the whole universe. So how are you going to make a cancer drug out of that? And so we have there's a complex chain of events that has been designed, and basically what these people were doing is they exposed some thorium, which is the common isotope of thorium, in a reactor, and gave it neutron exposure, and it underwent an alpha decay, and they come down by 4. So it went from thorium-232 to thorium-229, and this product has a half-life of 7.3 thousand years. And then it decays to radium-225, which has a half-life of 14 days, which goes to actinium-225 that has a half-life of 10 days, and then franconium that has a half-life of 4.8 minutes, and then astatine, 32 milliseconds, and then in about 3/4 of an hour, whichever way this goes, it decays, and each time it's releasing one alpha particle. And if you have it very, very tightly localized, these alpha particles will only move about the diameter of 1 cell. So you get a very concentrated dose of radiation. Now, So these are all the thorium isotopes that are possible. This is the one you would put in the reactor. This is the product you might take out and make a generator so that you can extract the radium and go on from there to treat the patient. And here's just one example. Now, this makes an impact on me because when I was a young doctor and I got my first job after residency, it was in the London Cancer Clinic. And my job was to look after patients who had very painful bone metastases. And we were trying various things that didn't work very well, like radioactive phosphorus in those days. And these patients would be just in terminal pain, terrible. And there wasn't that much we could do except give them more morphine. And you would do that until finally they got their wish, which was that their pain stopped. And so it was not a very satisfying job to be doing because it was a job of futility. But here is a patient with this kind of metastasis. Every black spot on this skeleton is a spot with cancer in it. And you can imagine how uncomfortable this particular person was. So he received 3 treatments with intravenous actinium labeled to what's called the prostate-specific membrane antigen, which localizes the radioactivity with great accuracy. And that happened in December. And then you can see that at that point he had a blood marker for cancer, which was 2,900 nanograms, which is very high. So after 3 rounds of treatment, 6 months later, this was his scan, and his cancer marker is now reduced to about 1/30,000th of what it was. And then he got 1 more round of treatment, and his cancer marker is undetectable. And I don't know whether he's cured. Time will tell. I would perhaps be claiming too much, but I'm just amazed by the potential that the alpha emitters are bringing to the field. And I think we'll be seeing many advances of this kind in my field in the future. Now, just for a little fun, neutrinos have no particular value in medicine, but they're around, and every time we calculate a dose for somebody with a beta emitter, like iodine treatments for a thyroid cancer or hyperthyroidism, we think about the neutrinos. The problem with when neutrinos were first found, there seemed to be that the law of conservation of energy was broken because the energy couldn't all be accounted for. And the spectrum of the beta particles was like this, that some particles had no energy and some had the maximum theoretical energy. And there was a guy by the name of Wolfgang Pauli who said, well, let's suppose there's some particle that we can't see and we can't measure it, we can't detect it in any way, but it takes away the energy to a variable degree. And somebody else said, well, good, let's call it a neutrino. And it's sort of a problem in a theoretical way. But Wolfgang Pauli wrote in his personal journal, he said, I don't know what I've done or whether it's a good thing. If I had said that the tooth fairy takes away the energy, then all my friends would have said that poor Wolfgang needs to go see a doctor. But because we called it a fancy name, we called it a neutrino, and it fits the calculation, I'm now famous. And he was never really happy with that explanation. And he didn't live to see the proof of his ideas because he died the year before neutrinos were first measured. Nowadays, we can measure neutrinos coming from the sun, and if you follow the science news a few years ago, Arthur MacDonald, who's a professor from Queen's University, received the Nobel Prize for the work he did in Sudbury. He has a mine that's 2 kilometers down below ground, measuring the neutrinos from the sun. And we know that neutrinos come straight. If you were to ask what's happening in the sun, if you're just looking at the sunlight, it would take you excess of 10,000 years to know, because the radiation that the sun emits at the core takes about that long to bounce around randomly until the energy is low enough that it comes out of the X-ray and gamma ray spectrum and comes into the visible light. But with neutrinos, if you're measuring neutrinos, you know in 8 minutes what's coming. And there are about 10 billion neutrinos per second per square centimeter coming through, and they're going through your body and not seemingly doing any harm. But it does make for some interesting possibilities. I have called this a picture of the sun taken at night, and I'll leave it to your imagination where the camera was pointed. And the fact of it is that you would point the camera at the sun, because this is made with an exposure to neutrinos. So you point the camera at your feet at night, and this is the picture you get. This was a time exposure that took 500 nights to collect. So it's that was 10 billion neutrinos per square centimeter per second all that time. So it's not a very efficient method, but we can. And a few years ago, there was a supernova not too far from us, and the people who were pointing detectors for neutrinos at the sky actually were able to pronounce on it being there for several hours before there was any evidence from the telescopes that this was going on. So there you go. Now, this is my last slide, and I just want to leave you with a little bit of light humor. There was a story going around that Kim Jong-un, the leader of North Korea, had made an announcement in his public square in Hanoi. And he said, well, Korea is going to get into the space program, and we're going to be the first to go to the sun. And the people all clapped. And then some intrepid reporter asked, isn't it going to be kind of warm on the sun? He said, no, we've solved that problem. We're going to go at night when it's cooler. And in Washington at that time was Donald Trump watching television. And he heard this and he said, what a doofus. Everybody knows there is no sun at night.
Oh.